Yes. Okay.
That's a good idea. Yes.
It's our pleasure to have the first talk on our seminar, which is just founded today, and it is even bigger honor that such a mathematician as Kristian is the first presenter on our seminar. I think most of you knows Kristian, who is this professor at the Norwegian University of Science and Technology, and who has many honors, including the membership of the Academy of Sciences and the presenter of the invited presenter of the Mathematical Congress in Berlin, and so on and so on. And now we will hear his talk. Please, Kristian, we are ready to hear you.
Well, thank you very much. Very nice to be with you, wherever you are. I think some of you are in Tbilisi and many other places. So this is I will speak about what is called Fourier interpolation with well, in general, and with the zeros of the Riemann zeta function. So please, could we go to the next slide? And I'm sorry for all this trouble. Well, so anyway, so the talk consists of three parts. I will explain what Fourier interpolation is, what is known, and how it is related to the uncertainty principle. And then we come to the zeta function. How does it fit into the picture? I will try to explain, to give you just a crash course, basically, on the Fourier duality that we have between the primes and the non-trivial zeros of Z. And then finally, we come to a new kind of Fourier duality, which is what we call Fourier interpolation with the zeros of the Riemann zeta function. So most of what I will speak about, and that is in particular pertaining to point 3, is based on a joint recent preprint with Andriy Bondarenko and Danylo Radchenko. So please. So I start with something to get you in the right mood here. Something very classical. So I remind you of the Poisson summation formula, which is one kind of expresses some kind of Fourier duality related to what we will speak about. So we have the usual Fourier transform defined with in this way, and we all know that we have this beautiful Poisson summation formula that relates the values of the function at the integers with the values of the Fourier transform at the integers, and for let's say sufficiently nice functions. So please continue. So one way to phrase this is to say that the tempered distribution that we get by taking point masses at the integers, call it mu, it satisfies it has its own Fourier transform. So mu hat is mu in the distributional sense. So more generally, when we have the situation that the tempered distribution, which is more generally a weighted sum of point masses over some sequence of points on the real line, for which the Fourier transform is of the same kind, over a dual sequence, lambda star, on the real line. When we have the situation, we say that we have that mu is a crystalline measure. So this is sort of a generalized version of the Fourier of the Poisson summation formula that has received some attention in recent years. So please move on. Now we ask a related but somewhat different question. We ask whether we can find pairs of sequences lambda and lambda star such that any nice function f can be recovered from the values taken by f at respectively f at lambda along with the values of f hat at lambda star. And we may also demand or we can ask whether this can be done with no redundancy, so that recovery fails if any point is removed from either lambda or lambda star. So the inspiration or what started this activity is a recent theorem of Radchenko and Viazovska, which reads as follows. The theorem of Radchenko and Viazovska says that well, we're dealing with even functions, just to make statements a bit simpler. So any even Schwarz function f, or maybe I should read it as it is written here. There exists a sequence of even Schwarz functions an on that of the real line taking real values, such that for every even Schwarz function f, we can write f as the sum of two series. The first series is we have the values f of square root n as the coefficients with respect to the sequence an, and in the other series we have the values of the Fourier transform f hat at the same sequence square root n, and then we take the Fourier transform of the ans. So both series converges absolutely for every real x, and the functions have interesting interpolatory properties. Essentially, they are at the square root m's. They are either 1 at square root m and 0 otherwise. Sorry, that's the n, yes. Well, it's written there, so it's clear enough. But there is something interesting going on at 0, namely these functions take the value 0 at 0, except for a very thin subsequence, the squares of the integers. So at the squares, I mean, when the index is a square, so an squared at 0 is -1, and the Fourier transform of an squared is 1 at 0. And this has a very interesting interpretation if we go to the next slide. It says that it really says that the Poisson summation formula in some sense sits inside of this formula, because if we now look at point evaluation at x, so we plug in the value x equals 0, then what comes out of the formula is the Poisson summation formula. So this is the sort of, well, this is in some sense explains why we have this special situation with the values at 0. So please move on. Yes, so we may think of then the Poisson. Oops, then you were too quick. So we may think of the Poisson summation formula as the representation of this linear functional of point evaluation at 0 in terms of the Fourier interpolation basis. And this is a point of view that I will come back to later when we discuss Fourier interpolation with the zeros of zeta. Okay. Now I would like to say some generalities about this kind of phenomenon. So please. So let's look at this situation. Now, instead of the square root ends of the integers on both sides, we considered the situation where we have two sequences, lambda and lambda star, on each side of the Fourier transform. We assume that there exist nice functions g sub lambda and h sub lambda star, so that we can write functions in a similar way. So, and we also require that this representation behaves as one should expect under the Fourier transform. So we have a similar formula for the Fourier transform then with the functions in the base in these two series just being replaced by the Fourier transforms. So in this situation, I do not want to assume any kind of minimality. In the previous situation, the theorem of Radchenko and Viazovska, we have this kind of minimality that if you remove just a single point, then everything and the formula is not, and you don't have any uniqueness anymore. Okay, but we don't assume that for the moment. So one thing that we can observe immediately, so please move on, is that whenever you have a representation like this, you can associate then point evaluation at x as a well, you can think of this as the delta measure at x minus then the delta measures at weighted delta measures at the sequence lambda, and the Fourier transform of that will be what you get from the other part of the formula. So this means that whenever you have this kind of Fourier interpolation formula as a byproduct, you have a continuous family of crystalline measures. So this business of crystalline measures is then closely related to Fourier interpolation. Okay, so please move on. So now I will explain what we found as a kind of general duality principle that is behind Fourier interpolation formulas. So when we are in the situation that I just described to you, we have these pairs of sequences along with the pairs of associated functions. Then we start from one side now, and we write down certain, or these two general Dirichlet series. So I split the sequence lambda star. So that's the sequence on the Fourier side. Okay, so I write down a sequence over the positive lambda stars, positive frequencies, if you like, with the weights. Well, the weights are the basis functions. So e to the minus 2 pi I lambda star z, that's e plus. And then I have e minus, which where the summation is over the negative frequencies. I mean, we split it in this way so that we get functions that are represent or are analytic in a half plane, right? So if these functions behave nicely, then this will represent a function that is analytic in a half plane. Both of these functions will have to admit meromorphic extension to the complex plane for every x. And now comes the crux of the matter is that these two Dirichlet series will, their meromorphic extensions will have simple poles at x and at the points of the dual sequence. Okay? And moreover, these two Dirichlet series are intertwined by a functional equation. So when they are a priori defined and make sense in separate half planes, but they are intertwined when we look at the meromorphic extension. They are intertwined by this functional equation that you see here. So E plus is equal to minus E minus. I am lying a little bit to you because there is something going on at zero, but this is so minor that I decided that I would just do it. So you have to put half weight on the zero if it is a frequency in your sequence. And of course, by duality, you have the analogous result if we reverse the roles of the two sequences and replace H sub lambda star by G hat sub lambda. Okay, so now we can move on. And so this is, whenever you have a Fourier interpolation formula, behind the scene, there is this phenomenon of these Dirichlet series with their meromorphic extensions and poles at the dual sequence. Conversely, whenever you have this situation, it is a fairly standard matter to check that this will give you a Fourier interpolation formula. You do, let's say, the usual tricks from analytic number theory of contour integration. So this duality that I described is exactly, so gives in some sense a characterization of this phenomenon, except of course that it's not so easy to find examples of this kind of situations. Okay, so then let's move on to the next slide. So now I come to the uncertainty principle. So it's very natural to ask what are the properties that you have to require from two sequences, lambda and lambda star, for something like this to happen. And Kulikov found recently that there is a kind of there is a density condition which is quite similar to what is known from time frequency analysis. So what we do is that count the number of points from one sequence, the lambda sequence, on the interval from minus t to t, and we count the number of the other sequence, lambda star, from minus w to w. And what Kulikov found, well, there are some technicalities, but under reasonable conditions, the sum of the sum of these two counting functions, n lambda of t and n lambda star of w, must exceed 4wt minus a small remainder term, which is probably log squared. Okay, but log squared to 2 plus eta of the product of the two. And this is something very similar to what is known in the signal analysis community as the so-called 2wt theorem. So it's a phenomenon that is well known. So if you could move on, please. So yeah, I say it here that this is the familiar Nyquist rate from signal analysis that you see, and it is therefore tied to the uncertainty principle. I put as an example what it gives in the case of the basis that we already saw with the square root of the integers on both sides. Then the counting function is, the two counting functions are 2t squared and 2w squared, and Kulikov's condition becomes t squared plus w squared larger than or equal to 2wt. There is a 2 here and not a 4 because we were just looking at even functions. So otherwise I should of course have had 4. Okay, so let me, before I come to sort of the main topic of the talk, which is to get zeta into the game. So there have been some subsequent work on things like this, and basically what is known is that as long as you don't require minimality, as we have in the Radchenko Viazovska situation, there is an abundance of formulas like this. So this, I give you a very brief overview of what has happened during these last few years. So Ramos and Sousa asked themselves, well, what if we replace the square root of the integers by something like n to the alpha and n to the beta on the two sides? They asked for uniqueness, so that vanishing on both sides would force the function to be 0. And they conjectured that this should happen if the sum of alpha and beta is less than 1. This was then taken up by Nazarov and Sodin, who were able to prove this and much more, and they joined forces with Kulikov, and they have now shown that in unpublished work that, roughly speaking, if you have infinite excess of density relative to what I gave you, the 4wt theorem, you can actually have a situation like this. But I should warn you that these sequences have to be fairly regular. But it's a fairly general result, so giving you conditions in terms of density for the existence of formulas like this. So please move on. This is very different. I didn't say anything about the proof of Radchenko and Viazovska, but I do it now. Their result relies on weakly holomorphic modular forms for the theta group. So it comes from a totally different world than let's say the classical analysis that is behind the results on this slide. So it's a very, very different approach, but it's really and that presumably explains that you were able to come up with this remarkable minimality that I think is very hard to catch if you stay just inside the classical situation. Okay, so but we are now interested in seeing if there are more situations where with this very special non-redundancy. Okay, so now we come to the zeta function. So I will now, as I said in the introduction, I will give you a sort of a crash course on the Fourier duality of the primes and the zeros of the Riemann zeta function, just to place this in context. Okay, so we start with the usual definition of the Riemann zeta function in terms of its Dirichlet series. I call this the additive definition. And then we have the multiplicative definition, which is the definition of zeta in terms of its Euler product, right? So both are defined in the half plane to the right of the one line. And well, you know, this goes back to Euler, who observed this, and then what next? So well, I will give you a few slides which just recalls the interplay between these two definitions and what leads to the duality that I'm talking about between the primes and the non-trivial zeros. Okay, so first is one slide where I just say what you get from the Euler product. So the multiplicative representation, what you do, if you please, could you continue? So what you do to get to the primes is that you take the logarithmic derivative of zeta. Then this is of course in terms of the Euler product, you get a Dirichlet series. If you and then you differentiate this Dirichlet series, and you get zeta prime minus zeta prime over zeta as the sum with the Dirichlet series with coefficients, the so-called von Mangled function lambda of n, which is log p if n is a power over prime and zero otherwise. And then the trick is to use the so-called parents formula to get the partial sum over of this von Mangled function lambda of n up to x. So you get the sum of the lambda n's up to x by taking this contour integral to the right of the one line. So you take zeta prime over zeta and you multiply it by x to the s over s. So it's an exercise to check that this identity holds. And if you do a partial summation, you get back to what you're really interested in. You're not interested in the von Mangled function, but you're interested in counting the number of primes, and to get back to that, you just do partial summation, and you get to the formula on the last displayed formula on this slide. So if you know psi of x, you know pi of x, which is what you're after. So this is what you get from the Euler product. Now from the Dirichlet series, the additive definition, you get the meromorphic extension, and you get the von functional equation that I guess you are familiar with. So if you multiply zeta by the so-called gamma factor, pi to the minus s over 2 times gamma of s over 2, you get something that is invariant under the variable s goes to 1 minus s. And from that you see the basic things, like zeta has only one pole, which is simple and located at s equals 1. By this relation 1 and the Euler product formula, the zeros of zeta outside of the critical strip are just a negative even integers. And yes, and then maybe we can move on. Yes, I'm mentioning this nice formula because I will refer to it later. So this is also something you get from the functional equation. You can use the argument principle, and you get this count of the number of well, I didn't say anything about the non-trivial zeros yet, but those are the zeros you have in the strip, and you can count them up to height t, and you get a very precise expression for the number of zeros, which is this sum known as the Riemann von mangled formula. It contains one mysterious term, which unfortunately I will not speak about, but it's an interesting term, S of t. This is essentially the imaginary part of the logarithm of zeta, the argument of zeta on the critical line. Okay, so everything here you get from the argument principle, the functional, and by Stirling's formula. Okay, yeah, this is not so relevant. So S of t is an interesting function, but we will not say more about it. So I think we just continue to the next slide. So now we are moving in the direction of what we're interested in. So what is it we have now? Well, we have two ways of representing zeta prime over zeta. On the one hand, we have it written as a Dirichlet series coming from the Euler product. And then on the other hand, since we by the functional equation, we know that it is up to the pole, it's an entire function, and an entire function of order 1 comes with an Adamar product. Okay, so you have an Euler product and an Adamar product, and if you combine these two things, you get an what is the, let's say, the beginning of everything here, which is on the left-hand side, the Dirichlet series representation of zeta prime over zeta. And on the right-hand side is the stuff that you get from the Adamar product, right? So you have a constant first, and then you have what comes from the pole at 1. Then you have a sum over the non-trivial zeros, rho. And then there is a term coming from the non-trivial, from the trivial zeros. That is, you see 1 over s plus 2n, and then something that makes things converge. So this is something that is valid when the real part of s is larger than 1. So this is the basic, this is the starting point for the duality. And one can rephrase this in different ways to get more explicit information. So I'm now showing you on the next slide the usual approach to the prime number theorem. Then you start from this contour integral to the right of the one line. And then you do contour integration. You move your line of integration to the left. And then you get, if you do the right things, you get an expression for psi of x, where now everything is about this second sum. Well, I actually cut it at the finite t. Okay, so then we get x to the rho over rho. And from that, if you just move on, I guess I should go sort of a little bit quickly here over this. Then again, I'm doing the same as I did before. I'm really interested in pi, so I go back in the same way as before, and you see that that you get an expression for the remainder term e of x in the prime number theorem, which is expressed in terms of the zeros of the Riemann zeta function, and you see the importance of the real part beta of rho. Rho, I remind you, are the non-trivial zeros, and beta are the real parts. So if all the betas, well, you know, if they are on the critical line, that would mean that this becomes as small as it could be, the Riemann hypothesis. Okay, so if you could just show the rest. Yes, I wrote it here that this is the Riemann hypothesis. Okay, but this is not, well, we are interested in it, but now let's see. So this is sort of the usual way to get from this formula that I had on the previous slide. But there is another way of looking at it, which is sometimes quite useful, and it's certainly intrinsically interesting. Now, when we got to the previous slide, what we actually did was to use Perron's formula and a very specific function. If you remember Perron's formula, in this integral, we have x to the s over s. So instead of plugging in that, we can plug in basically any test function, h of z. So this is something that behaves sufficiently, it's analytic in the critical strip, let's say plus epsilon, half plus epsilon, and then it decays sufficiently for everything that I'm saying to make sense. To make it a Fourier analytic statement, I actually now send the critical line, which is vertical to a horizontal to the real line, just to have a statement that makes sense as a Fourier analytic statement. Okay, so we just send the critical line to the real line. And then if we plug in this, instead of doing, well, we are doing the same as in Perron's formula, but we replace x to the s over s by this test function. And what comes out, if we use this duality that I showed you 2 slides ago, on the left-hand side, we get the values of h at the zeros row. Well, since I sent it to the real line, it's rho minus a half over I. Then we get the contribution from the pole. It has been symmetrized now so that we get one part from the pole and in some sense one part from the first pole of the gamma factor. So we make it symmetric. Then there is an integral which comes from the gamma factor of the functional equation. And then we have a sum over the values of h hat at log n over 2 pi. And we sum then only over prime powers because we have the von Mangled function there, lambda of n, which is non-zero only when we have prime powers. So in the last sum, you should really think of it as a sum over the primes because the higher order powers don't really play an essential role. So you can certainly think of it as a sum over the primes. Okay, so then I think I wrote here what I already said, that we get it by replacing x to the s over s in Perron's formula by this more general test function. And we use the symmetry expressed by the functional equation. Okay, so now what we will do is to formulate another Fourier duality relation involving the non-trivial zeros of z of s. Now, in the previous case, I didn't really care about whether there is whether the zeros of zeta come with multiplicity, but for what we unfortunately we have to take that into account. Of course, people believe that all the zeros are simple, so I could of course assume that, and the formulas would be nicer. But anyway, let's count the multiplicities in this way. M of rho is the multiplicity of a given zero. Then I will look again at test functions, and I'm now require that the test functions that we will be using, or well, the functions that we will consider, they are again analytic in the critical strip plus epsilon, and they decay so that this integral that I wrote up is finite. Okay, this weighted integral. And then we will also say that functions on C that decay, well, like Schwarz functions, basically, we will say that they are rapidly decaying. Okay, so then we have our theorem on the next slide, I think. So this, well, it's not as bad as it looks at, as I hope. So you see now you should probably focus on the formula, the first formula there. So f is now a function in this space H1. And you see that we express it now as two sums, as we have seen before. So you have, to the left, you have f hat at log n over 2 pi, over 4 pi. And there are basis functions, un of z. And then on the other side, you have the values of f at the non-trivial zeros of zeta. And unfortunately, because we cannot exclude the possibility of multiple zeros, we have to take that into account and take derivatives accordingly. And then there are basis functions also, of course, in the second sum. I call them v rho sub j. There is a small issue with convergence in that sum, so therefore we have to be a little bit careful when we sum the series. But we can do it in such a way that this converges nicely, and the functions, basis functions un of z and the v's v rho j. They have precisely the kind of minimality properties that we like. So they just take the right value at where they should be, let's say 1, and then otherwise they are 0 at all other points. And then by that I mean that both the function and the Fourier transform, of course, are 0 where they should be 0. So they have exactly the interpolatory properties that we really would like to see. Okay, so that's the theorem. And what I would like now to say is I want to compare this theorem, this Fourier interpolation theorem, and the Riemann wave formula that I had before. So both of them, I cannot say much about the proof, but both of them rely crucially on the functional equation. It's absolutely crucial for both functions. But there is a distinction, a principal distinction between them, and that is that the deduction of the Riemann wave starts from the Euler product representation of zeta of s. Remember that we had this duality where we used the Euler product and the Hadamard product. The Fourier interpolation formula is tied really to the Dirichlet series representation of zeta. So I like to think of it as that we have two formulas that express respectively a multiplicative and an additive duality relation between the zeta zeros and a very distinguished sequence of integers. And if you move on, I think I say a little bit more. And what you should notice is that the Riemann wave formula, I will come back to it, I think, on the next slide. It is really the sequence of integers involved in that formula is a very thin subsequence of the corresponding sequence appearing in the Fourier interpolation formula. If you remember a few slides ago, we had log n over 2 pi in the Riemann wave, and we had log n over 4 pi in the Fourier interpolation formula. So it's really like going from n to n squared. That is the difference between the, let's say, the thinness that sort of expresses the thinness of the sequence involved in Riemann wave compared to the one we have in the Fourier interpolation formula. So I think that the next slide, if I remember correctly, says a bit more. about how we may think of this Riemann-Weil, the classical duality between the zeta zeros and the primes, how it is related to our formula. So we may think of Riemann-Weil, this formula that that I showed you before. I'm now making a similar. I'm trying to make an analog to what we had with the Poisson summation formula. Okay, so the Riemann-Weil formula you can think of as a representation of a distinguished linear functional. So what I've done here is I've just taken out of the Riemann-Weil formula the stuff that comes respectively from the pole, that is the h of I over 2 plus h of minus I over 2 plus this integral that came from the, let's say, the gamma factor. So this is, of course, a nice functional on the space H1. And the Riemann-Weil formula then drops out as the representation of this linear functional with respect to the basis functions of our Fourier interpolation theorem. So in a similar way as, it comes on the next slide, in a similar way as we could see Poisson summation as sitting inside the Viazovska, Radchenko and Viazovska theorem, you can think of the Riemann-Weil formula as sitting inside of this Fourier interpolation formula that we found. And I also like to think of them as both of them, of course, are attached to or owe their existence even and importance to an inherent algebraic structure, which in the case of the Poisson summation formula is additive, it's periodicity. And of course, in the Riemann-Weil formula, it's really a multiplicative structure. Okay, so let me just then mention that Kulikov also has something to tell us. His condition now can be applied in the sense that you can see what does it tell us about this special situation where we have the zeta zeros and this sequence log n over 4 pi, which we had on the other side of the Fourier transform. And what comes out is the following. He tells us that, well, if you, of course, you get a general inequality for all possible pairs of T and W, but if you choose, let's say, the right W, you will see that you get down to essentially the Riemann von mangled formula. So you see the Riemann von mangled formula appears then, if you like, as some kind of, well, you could call it uncertainty principle. In any case, I find this a quite interesting relation that you can obtain. Well, he doesn't get exactly the Riemann von mangled formula because it's an inequality, but it is interesting to see that you actually get down to this precise relation, I think. Okay, so what else is there? I think I have some closing remarks. So I didn't say anything about proofs. They are, as I said, they really come from modular forms, or what I call weakly holomorphic modular forms, and that's really the tool that you need to build these Dirichlet series that I told you about. I mean, as I told you, whenever you have a Fourier interpolation basis, there is behind the scene a Dirichlet series and a kernel. I mean, it's really a kernel because there are two variables. So these kernels, to build them, you need this machinery coming from these modular forms. technology. So a good part of our work is about getting precise estimates for the coefficients of these Dirichlet series kernels. And then, of course, when you have all this machinery up, you can do similar things for a large class of L functions, if you like. But I think it would be very interesting if one could. I mean, we have now two situations where these kinds of miracles happen, that you have Fourier interpolation basis with no redundancy. So it happens in the square root n case studied by Radchenko and Viazovska, and it happens with the zeros of L functions and a corresponding sequence on the which basically will be like log n times some constant. Okay, so but could there be other sequences for which this happens? So this, I think, it would be very interesting to find out more about. And of course, a question that is very natural to ask is whether this can be, let's say, useful. And what do I mean by useful? Well, useful here would mean, has this something new to offer when you're studying the zeta function? You are, after all, you are studying the zeta function because you want to find out something about the primes and things like that. Would it be useful? I don't know. I think for the moment I can only say that it remains to be seen. But in this business, I think also that you have to be patient, and you shouldn't expect progress to come always very rapidly. So we will see. I added as a last point something that Freeman Dyson said in a talk that he gave in 2008, and I think it was called Frogs and Birds. And he suggested that one could approach the Riemann hypothesis by classifying crystalline measures, and this, of course, is related to what we see in the Riemann wave formula. My conclusion after what we have done is that I think that what we have done adds further evidence to the common belief that such a classification would probably be very difficult to obtain. Okay, so thank you very much for your attention.
Oh, thank you, Kristian. Just contrary. So for your very interesting talk, and I think to evaluate the importance of your results, it's very early. It will be seen in future, perhaps. The results are very interesting. I think with a very important contribution to this study. Okay, now maybe somebody has a question.
I have a question. I have a question, if I'm allowed to.
Eugene?
Yeah. Kristian, perhaps maybe I was concentrating on pressing the button, so
Yes,
I missed something. But in your main theorem, is it conditional on the Riemann hypothesis? So you don't care?
No, it's not. It's not.
It's not. So those non-trivial zeros, when you have 0 minus 1/2, they will still, they can be not sort of, they don't have to lie on the.
No. It's no. Of course, yeah. It's not conditioned on the Riemann hypothesis, but I would say that if you look at the applications of this Riemann wave formula, they are usually, I mean, I think that so far this formula can be useful on the Riemann hypothesis, but it's very hard to get non-trivial information about the zeros from the formula. I mean, it's very hard to get non-trivial information out of it. And for the moment, we are in a similar situation with our formula. Very hard to get such information out of it.
And another question, if I can abuse my sort of host privileges. Basically, you mentioned Sodin's work. I know a little bit about Sodin's work, but when you talk about crystalline measures, is any work of Levski of any relevance to this business?
I mean, I haven't really tried to make this connection, but I think it would be interesting to try to connect these two worlds. That's basically all I can say. So what we have observed is that whenever we have the situation, we have just this abundance of these measures, but they usually have different perspectives. So, and they, of course, they come up with different kinds of measures. But it would certainly be interesting to try to connect these two worlds. Yes.
Okay. Maybe some other participants have some questions.
Can I have a question?
Yes, please.
Thanks for the nice talk. My question is, you mentioned this conjecture with alpha plus beta strictly less than 1.
Yeah.
But in Radchenko and Viazovska, they have square root of n, so 1/2 plus 1/2 equals 1. Why not less or equal to 1 in that conjecture?
Yeah, because it's very hard. It's like I say, that this thing that goes on exactly on the edge. I mean, when you have exactly, or you're exactly on the critical density, and when I speak about critical density, it is of course with reference to the Kulikov's theorem. So this is a very delicate situation, and it seems very, very hard to deal with it. Did I disappear now, or something happened on my machine? But so it's virtually impossible to reach it, except in this very special case of square root n, where you have a certain technology at your disposal that allows you to do it. I mean, they are using. Nazarov and Sodin are using classical Fourier analysis, complex analysis, to some extent functional analysis, and with these tools, it seems very, very hard to get down to the critical density.
Okay, thank you.
So
I have a question.
Questions? Sorry.
I have a question directly related to the now. First of all, I mean, if you assume that the Riemann hypothesis is correct, then we would have a very symmetric formula here.
Oh, Elias, it's very difficult to understand you. Maybe something with microphone?
Can you hear me at all?
Yes. Now we hear it better.
Okay, then I will go a bit closer to the microphone.
Yes, perhaps.
So if Riemann hypothesis is correct, then we have a very nice symmetric formula where on the left-hand side, if I interpret it correctly, the trivial zeros somehow are involved, and on the right term here, we just have the non-trivial zeros.
Mm-hmm.
Is this interpretation correct? I mean, this is fascinating for me because
no. The trivial zeros are not really in the formula.
They are not in the formula, but this term comes from the trivial zeros or not? Is it somehow related? I mean, they do not appear here.
No. They don't. They come from the Dirichlet series. You could say that you have the well, it's a little bit more complicated than what I'm saying now, but it's a close enough approximation. So zeta comes with a Dirichlet series.
Okay.
And then it is the frequencies of n to the minus s. I mean, it's e to the minus s log n, right? So that's where the log n's come in. So it comes from the terms of the Dirichlet series. So that what I said now was a little bit of cheating, but close enough, I think.
Okay, but that's a bit. I mean, it would be even more miraculous if this the first sum would be related to the trivial zeros.
Yeah.
And the second question is, what do you know about the basis function? How
we know something, and I mean, but not quite as much as we would like to. And of course, if we knew more, we could have a hope to actually make this useful.
Okay.
So it is yeah. No. We know something, but not enough.
But I'm convinced it is useful. So yeah, at least I'm very much impressed by this.
Yeah.
Okay. Thank you.
Okay. The further questions, please. Maybe I have one question. I was interested in the first part of your talk in these expansions of function according to these lambda and lambda star sequences and the functions, appropriate functions. Do you have some conditions for these functions when these expansions are possible?
Well, that is, I would say, what Sodin, Nazarov, and Kulikov are doing. So they have pretty strong conditions, I would say, for this to happen. So yes, so
almost necessary and sufficient, you mean?
Yes. Well, this is well, they have. Well, Kulikov comes with a necessary condition, and then they have pretty strong sufficient conditions.
Oh, nice. Mm-hmm. Okay,
yes.
Thank you.
And I would say for me, it was a bit surprising that they could do it in such generality as they do. I find it quite remarkable.
So, but you profited from it, yes. Okay.
Yes.
Okay. Then, if there are no further questions, we have to thank Kristian again. Thank you, Kristian, for this very interesting talk and for this communication. And meet you after 2 weeks on our next seminar.
Okay. Thank you very much. Thank you very much.
This will be given by
Michael Sodin. So our next meeting will be
few days.
Our next speaker will be Michael Sodin. Hasn't decided yet on the topic of his talk. So I kind of assume that he perhaps would be talking about the topic that is related to his talk, but he thinks I'm sure whatever he decides to talk about is very interesting. So see you all in 2 weeks' time.
Thank you. Goodbye.
Goodbye. Hi, everybody. Thank you for participating.